There are infinitely many summation formulas that you can see and use in practice. However, it turns out that for a lot of code analysis, which is what we are going to focus on, and for a lot of practical applications, there are some ones that will show up much more commonly than other summations. Some of these we've already proven. We've proven the arithmetic sum formula, which is the first one. We've also proven the finite geometric sum formula. There's other ways to write that down. We proved that it was equal to the second fraction. The first fraction is the same thing, but if you factor out a -1. So that's another formula. Two other very common formulas are the sum of cubes and the sum of squares. Both of these can be proved very similar to what we did before. There is no real difference in either of the analysis you'd use there. You would use induction. You would then do the exact same procedure that we used before. The last one I'll comment on is the infinite geometric series formula, which is just taking a limit as n goes to infinity of the finite geometric sum. If you remember, infinite series, you can find out what they converge to by finding the limit of the partial sums. The finite geometric sum is the partial sum of the geometric series, so you can do that by taking the limit as n goes to infinity. However, the formula only holds when the absolute value of r is less than 1. You might ask, we're going to be analyzing code. Why on earth would an infinite series show up? We will see that later when we start analyzing the complexity, the asymptotic complexity of these summations. So this formula, while it seems like why on earth would you ever need that, it shows up more often than you might think, and we will see that as we are analyzing various summations. A useful skill we will try to use these formulas for is that we want to be able to find exact expressions for summations without having to formally prove them with induction. Induction proves to be incredibly tedious to do when you already know mostly what it looks like. So we will see that these formulas can be used to find closed form expressions for slightly more complicated summations.